You clicked on this video because you heard about NVIDIA's new StarElastic release, and you want to know what it actually means for your infrastructure. The real problem is that the industry has been stuck in a brutal trade-off for years. You either build a massive model for high performance and waste money on hardware you don't need, or you build a small model for budget hardware and sacrifice the reasoning power that actually matters. This new technology promises to end that compromise entirely. By the end of this explanation, you will understand how a single checkpoint can dynamically serve different hardware constraints without any retraining, fundamentally changing how you think about model deployment. For the last several years, the standard approach to deploying large language models has been rigid. If you needed a 30 billion parameter model for your cloud servers to handle complex reasoning tasks, you trained it, packaged it, and deployed it. If you needed to run something on a smaller device with less memory, you had to train a completely separate 12 billion parameter model from scratch. This created a fragmented ecosystem where engineers spent their time managing dozens of different model versions, each requiring its own storage, distribution pipeline, and fine-tuning cycle. The cost of this approach is staggering. You are paying for the same underlying intelligence multiple times, just sliced into different sizes, and you are constantly retraining to adapt to new hardware constraints. NVIDIA's Nemotron Elastic framework challenges this entire paradigm by introducing a concept called zero-shot slicing. This is not a compression technique in the traditional sense. It is not about taking a large model and squeezing it down like a compressed file. Instead, it relies on a specific architectural design where smaller models are embedded within a larger parent architecture as active subnetworks. Think of it less like a set of nested Russian dolls and more like a single massive library where every possible book size is already written and shelved in its correct place. The 30 billion parameter model contains the 23 billion and 12 billion variants as latent subgraphs within its own structure. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The mechanism that makes this possible is a runtime dynamic router. When you deploy this system, you load a single monolithic checkpoint into your memory. Depending on the available resources of the hardware at that moment, the router activates the specific subnetwork required. If a high-end server is available, it routes the request through the full 30 billion parameter path. If a budget device connects, it instantly activates the 12 billion subset. This happens without reloading any data and without any latency penalty associated with switching models. The system simply toggles which parts of the network are active. This approach eliminates the need for the traditional teacher-student training loop used in model distillation. In standard distillation, a large model teaches a small model, and the small model often loses nuance in the process. Here, the smaller variants are not distilled copies. They are the actual, full-capability reasoning paths of the larger model, just restricted to their specific parameter bounds. The 12 billion variant is not a watered-down version. It is the 12 billion parameter subset of the 30 billion model operating with full reasoning capabilities within its size constraints. This means you are not trading quality for size. You are trading available compute for available size, but the intelligence remains consistent across all tiers. The efficiency gains from this architecture are quantifiable and substantial. Because you only need to train one large model to generate all the variants, the data engineering trade-off shifts from storage and distribution efficiency to compute density. The research indicates a cost reduction of up to 360 times compared to training distinct model families from scratch. This is because you are only using roughly 110 billion training tokens to generate the entire family of models. Furthermore, this method yields a 7-fold improvement over standard compression techniques, which often degrade performance significantly. The underlying technology relies on a hybrid architecture combining Mamba and Attention mechanisms. Mamba is a state space model that is highly efficient for processing long sequences of data. By integrating group-aware state space models with traditional attention layers, the system can dynamically route information through the most efficient paths depending on the active subnetwork. This allows the system to maintain a constant deployment memory footprint regardless of which model size is currently active. The hardware does not need to be reconfigured. The software simply exposes the latent capacity that was already there, waiting to be utilized. This shift has profound implications for the role of the engineer. In the past, an engineer's job involved selecting the right model version for a specific device and managing the versioning of those models across different environments. That work is now becoming obsolete. The bottleneck is no longer model availability or the need to maintain separate binaries for edge versus cloud deployments. The new bottleneck is the intelligence of the slicing algorithm and the efficiency of the inference engine, specifically the NeMo framework that powers this technology. Engineers are evolving from model selectors to runtime orchestrators, focusing on how to allocate resources dynamically rather than how to package static artifacts. Consider the practical impact of this on a heterogeneous inference cluster. You might have a mix of high-performance GPUs in the cloud and smaller, lower-power chips on edge devices. Previously, this required maintaining two separate model families, doubling the storage costs and the complexity of updates. With this elastic architecture, a single update to the parent checkpoint automatically propagates to all variants. A fix in the reasoning logic for the 30 billion model is instantly available for the 12 billion model because they share the same underlying weights. This solves the fragmentation problem that has plagued the industry for years, allowing a unified system to scale performance linearly with available GPU memory. The specific release featuring 30 billion, 23 billion, and 12 billion reasoning models represents the first concrete application of this Nemotron Elastic framework to the reasoning domain. While the broader technology has been demonstrated, this specific configuration proves that the many-in-one architecture works for complex reasoning tasks, not just general language generation. It demonstrates that you can have a single artifact that serves as a universal solution, scaling up or down based on the immediate needs of the workload. This is the end of the one-size-fits-all trade-off. You no longer have to choose between performance and flexibility. You can have both, dynamically, in real time. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.